So there's a lot to grasp. We should let's define these processes. So we have N, we have 1.75 mole, and again, it's a monatomic ideal gas. So this would most likely be a gas from group 18, the noble gases. They can exist, they can exist by themselves. They don't need to be bonded to one another. Therefore, they are considered a monatomic, one atom ideal gas. For process A, we can say that pressure sub 1 equals pressure sub 2, and this is going to equal 425 newtons per meter squared. We can say that the volume sub 1 is going to equal 2 meters cubed, and then the volume sub 2 will equal 8 meters cubed. For process B, we have two-step. This is a two-step process. So we first have an isothermal expansion. Again, temperature doesn't change. That's what isothermal means. And expansion, this means that the volume is increasing. However, it's isothermal. So that means that PV is going to equal a constant. Because again, the number of moles in this gas, of course, does not change. So this would be from state 1 to V2, so the second volume. And then the second step would be an isochoric meaning constant volume. So this will be an isochoric increase in temperature to state 2. And again, this will be a two-step process for the process B. So now they're asking us first of all, part A is asking us to draw. So let's get a new workbook and say that we have pressure here. This is going to be in terms of Newton per meter squared, and then we have a volume here in cubic meters, and we'll just put some quantities 2, 4, 6, 8. So we can just say 2, 4, 6, 8 for that, and then we can have 100, 200, 300, 400. Yeah, so 100, 200, 300, 400. So we first have an initial volume of 2 cubic meters, and then initial pressure of 400 Newton per meter squared. So 425 rather. So 425 would occur just above 400. So we can just say right here approximately. And then this is a isobaric process, so pressure does not change, and we're expanding from 2 to 8 cubic meters. So it's about here, and we can just draw a line, draw an arrow, and then we can label this A. So this is all we know at this point. Let's find the work in part. Let's find the work and the change in internal energy of process A. So that's for part B. They're asking for the work in process A. So this will be P delta V. And this is, of course, going to equal 425 and then 8 minus 2. So we have 2,550 joules of usable work. Now, we know that PV equals nRT, and we know that delta U depends on delta T. So we can say that delta U is going to equal the degrees of freedom over 2 times nR times the change in temperature. And the degrees of freedom, this is a monatomic ideal gas. So rotating the ideal gas, the monatomic ideal gas, would not change its orientation or how it looks. However, translationally, we have 3 degrees of freedom. So this would be 3 nR delta T over 2. And we can say that this is going to be equal to 3 nRT sub 2 minus nRT sub 1, and we can divide this by 2. We can substitute and say delta U is going to be equal to 3 over 2, and then here we can say P2V2 minus P1V1, and this is going to equal 3 times the work over 2, or 3 times 2550 divided by 2, and this is giving us 3,830 joules. So this would be the change in internal energy, and this would be, of course, the amount of work done, all in process A. This is all for process A. So for part C, it's asking us to draw the process B on the on the graph. So for isothermal expansion, we can say that pressure is going to be inversely proportional to the volume. So if we were to say this, we can say that if a volume expands by a factor of 4, that means that P will drop by a factor of 4. Now, if we were to draw this on the graph, we can say that we can go from, basically, we're going to drop by a factor of 4, so it's going to be really close to 100. And it's going to return from state 1 to volume 2, defined by the process B, from state 1 to volume 2, and again, pressure is dropping by a factor of 4, which means that we have this curve here. Apologize for it not being perfectly parabolic, or perfectly curved, rather, not parabolic, and we can just label it B. And then the second process is an isochoric increase to temperature to state 2. So this will simply be isochoric, so we have a straight line up to state 2. We can label this B as well. So this would be the two processes labeled on a PV diagram, and we have C. And so part D is asking us for the change in internal energy of both processes. However, the change in internal energy only depends on the change in temperature, which means that the change in process B will equal the change in process A, and this is going to equal 3,830 joules. So because both of these processes end up here at state 2, this dot right here, A takes a one-step route and process B takes a two-step route. However, the initial and final temperatures are the same for both of these processes. Therefore, the change in internal energy for process B will equal the change in internal energy for process A. We already found that here, again, 3,830 joules. So we can just set this equal and say that the change in internal energy of process B will be equal to 3,830 joules. So the change in internal energy will be the same no matter what process you're taking. That's the end of the solution. Thank you for watching.